Okay, folks, sorry for the bit of the hiccup there. Actually, I made a mistake in terms of what we were seeing right before we left, and then I got booted off. So let's go back and kind of fix that real quick. So the first thing, remember, we had to write e to the natural log because those two are inverses of one another, and the natural log will allow us to pull those things on down. So we get this raised to the 9x. The big thing here, this one's just a little bit more complicated with the derivative. So we get e to the limit as x approaches infinity. We can now pull that 9x down. So you get 9x natural log of 11x over 11x plus 6. Okay, so now we can pull that 9 out in front of the limit because that is just a constant and it won't be involved in our derivative. But with the x, we can't have infinity times natural log of 1 is 0, by the way. So that won't quite do it for us. So the way to kind of approach this thing now is we got to rewrite it and write it in an indeterminate form. And so what I was trying to do before was rewrite it where we go 11x minus 11x plus 6 for the sake of having an easier derivative, but it wouldn't work out because we'd have infinity over 0 in this case. So we got to work with this because now this is 0 over 0. That allows us to use L'Hopital's rule. This is the one case where you're really going to have to use L'Hopital's rule. And the reason why, notice if you go back to this, we have x's in our base and we have x's in our exponent. So that's kind of the trick there in terms of what's going on. So this becomes e to the 9. And now with L'Hopital's rule, I'm not claiming it's going to be pretty, but you get 1 over 11x over 11x plus 6. And then we're going to have to use the quotient rule to take the derivative of this thing. So that becomes 11x plus 6, because it's chain rule is what's happening here. 11x plus 6 squared times 11x plus 6 times 11. Wowzers, right? And then we have minus, it'll be 11x, because we're writing the numerator, and then times 11 as well, because the derivative of the denominator is 11. So kind of nasty, I know, but hopefully that doesn't look horrible to you. And the derivative of 1 over x, that's x to the negative 1, so that's going to be just negative 1 over x squared. Okay? And we have all this is the limit as x approaches positive infinity. So a fun one, nonetheless. So we have e to the 9th power. Now let's brush up this whole bunch of business. So notice the 11x plus 6 squared, that'll cancel off with that 11x plus 6, at least the square will. And so we'll have the limit as x approaches infinity of, we'll have a negative symbol out in front now. And the reason why, because we have that here, let me highlight that. So this is the cause for negative. Okay. Now, taking a look at this part, where do we go from here? So notice this is 11 squared times x plus 66 minus 11 squared times x. Okay, so it looks like the 11 squareds times x will cancel, and so we'll be left with 66 x squared, right? The x squared comes from moving this up top. And then down below, what we're left with is 11x plus 6 times 11x. So 11x times 11x plus 6. Wowzers, right? So this makes e to the 9th, and then we have the limit as x approaches infinity, and this would be negative 66x squared, and then times 11 squared is 121x squared. So 121x squared plus 66. If you notice, the really cool part on this one, that derivative wasn't fun, but we get the job done. So this becomes e to the 9th, and then you're just looking at, since both of these have x squareds, you'd multiply by 1 over x squared, but essentially they cancel, or you can use L'Hopital's rule twice if you like, whichever you prefer. This is negative 66 over 121. Well, both of those have a common factor of 11 in them. So this is e to the 9th to the negative 6 over 11. And so that makes e exactly what I'm sure you were thinking of off the top of your head. E to the negative 54 over 11 is our final answer. Right? Kind of a crazy one. It turned out to be pretty neat in terms of what it comes down to. But remember, the key component, you had these two things. You have an exponent in the base, exponent in the, or exponent, variable in the base, variable in the exponent, and then that means you had to use an e and a natural log to bring that exponent on down, and then use L'Hopital's rule. You will see something along these lines. Okay, now moving forward into, for the figures below, we have the limit as x approaches a of f of x over g of x, if f of x is shown by the blue curve and g of x is shown as the black curve in each problem. Okay, so let's take a look, and I put in some values here. So in this case, what happens? Well, that means you get 0 over 0, right? Because if you look, both points are at 0 at a, right? So we can use L'Hopital's rule. So L'Hopital's rule states that we can write this as the limit as x approaches a of f prime of x over g prime of x. And so notice that means that this should be f prime of a over g prime of a. Well, how do we figure that out? Well, you draw the tangent line. So in this case, our tangent line, what is the slope of this? Well, what that tells us is f prime of a equals 0. And then if you look at the other case, so this is at a, it is a line, right? So g prime of a, oh, I'm sorry, I said f prime of a. F of x is shown as the blue curve, so f prime of a, that's not f prime of a, that was g prime of a equals 0. And then we have f prime of a is the blue curve. And so the blue curve will just have, we know that's a negative slope. So just keeping that in mind. So this would be negative, some negative number over 0. Now, are we approaching 0 from the left or from the right? Well, notice either direction you're increasing and decreasing, so you'll get both directions. So this thing is going to blow up in terms of, we'll actually be approaching a case where this does not exist. Because as we approach a, so let me do it this way. So when we take this, the limit as x approaches a, limit as x approaches a from the left of f prime of x over g prime of x. What's happening? We have negative, and then you have 0. As we're approaching this, notice our tangent lines are decreasing, so we have negative again. But it's close to 0. So this thing equals positive infinity. And if you look at the other scenario, limit as x approaches a from the right of f prime of x over g prime of x, notice in that case, we're going to get, once again, the negative. But if we're approaching from the right, we have an increasing part of the function. So this is going to be positive close to 0. So that means this thing is going to negative infinity. And so that means our limit does not exist in this scenario. Okay, so now let's get to the crazy, well, that was the crazy one that does not exist scenario. Now let's get to another that's a little bit more interesting. Let me see if I can fit that in here. The process is pretty much going to be the same, but we'll finally get an answer to something here that's not a does not exist scenario. Okay, so notice we have both curves have 0 and 0. Right? F of x is shown as the blue curve. Sorry for screwing that up in the first place. I got to be paying a little bit more close attention. So this means we have L'Hopital's rule. So you get f prime of x over g prime of x. And so that means we can look at f prime of a and g prime of a. Okay, so f is the blue curve. Notice it's downward sloping. And so now we need the slope somehow, some way. Well, looks like we have a plus 1. And we said that was negative 1. So this is a plus 1, comma, negative 1. And notice the y value here. You have a, comma, 0. So first off, for the f prime of a, we can find that slope. That would be negative 1 minus 0 all over a plus 1 minus a. Now for our second scenario, notice we have the g prime of a. We're going to look at the slope at a at this point. Well, it's a line, so we can have that same exact value. So we can go a plus 1. Notice in this case is positive 1. Right? And so in this case, we get 1 minus 0 all over a plus 1 minus a. All right, so what happens? Well, a plus 1 minus a, the a's will cancel in both top and bottom, so we're left with a negative 1 over positive 1. And then down below we'll have 1 over 1. And so negative 1 divided by 1, and then all of that's divided by 1, so this is just negative 1. And so this whole thing is just negative 1. Questions on that? So you're seeing L'Hopital's rule and how we can use derivatives to look at graphs and use derivatives as well along with that. So L'Hopital's rule can be applied all over the place. So next one, we have shown below are 6 statements about functions. Match each statement to one of the following functions shown below, which best matches the statement. Okay. So I see a whole bunch of left and right and all that business. Remember, we can start to sort these out pretty quickly. Some of the information you can get. Limit as x approaches 4 from the right and 4 from the left. So in this case, limit as x approaches 4 from the right of f of x. That's going to equal 16, or yeah, 32 minus 4 times 4, so that's going to be 16. Limit as x approaches 4 from the right of f of x equals, or 4 from the left, I'm sorry, of f of x equals 4 times 4, which also equals 16. Okay, so we have 16 and 16, so the limit does exist at x equals 4, but notice f of 4 equals 0, and that's by this mark right here. So what that tells us is that this is not continuous. At x equals 4. But we do have a limit as x approaches positive 4 of f of x equals 16. So the limit exists, but it's not continuous at x equals 4. So this one, let's look at all of them. Limit as x approaches 4 from the right f of x, and limit as x approaches 4 from the left of f of x both exist and are finite, but they are not equal. Well, they are equal, so that doesn't work. The graph of y equals f of x has a vertical tangent. Nope, that's not the case. Limit as x approaches 4 from the left of f of x equals, nope, not the case, because infinite, we want it to be 16. Notice this says 4 from the left does not exist, so we're not that scenario. Limit as x approaches 4 of f of x equals infinity, not that scenario, so it actually is, number 6 is A. Okay, so for our next scenario, this one actually isn't so bad. It's just the graph of, so first off, let's do the, whoop, that's supposed to be flat there. Here's the graph of 1 over x squared. And what we've done is shift 4 units right. Okay, so that means rather than having to do the left and right hand limits, we have the limit as x approaches 4 of f of x. If we shift that 4 units to the right, it will be positive infinity. Okay, questions on that part? So notice that does satisfy number 5. Let's see, does it satisfy any other conditions? No. So looks like B is number 5. Okay, so we can do, this function is continuous, so we have f of 4 will be the limit as well. So we get f of 4, you plug that in, you get 0, and that equals the limit as x approaches 4 of f of x, and so that should be equal to 0 as well. Now, limit as x approaches 4 from the right, 4 from the left, both exist and are finite, but they are not equal. That's not correct. The graph of y equals f of x has a vertical tangent line. Well, we'd have to do another check for that, or we could draw the function, which isn't too bad either. If you draw the function, you shift it 1, 2, 3, 4. It's basically the cube on its side, and it looks like that might be our candidate. When you take a look, so just to verify this, we'll go f prime of x equals, this will be 1/3, and you'll get the cube root of x minus 4, and that's, it should be to the negative 2/3, so the way we write that is write it in the denominator. So what happens here? Well, that means, and then we can multiply by the derivative of the inside, which is just 1, so that's why you don't see me writing that there. But so it means that the derivative is not exist. So f prime of 4 does not exist. Now, to be a little bit more conclusive here, notice as we approach 4 from the left, this thing is blowing up towards positive infinity, and as we approach 4 from the right, because we're squaring this both times, it's blowing up towards positive infinity. So this means a vertical tangent. And we can kind of see that by the graph too. So C goes right here. Okay, let's take a look at D. You get the limit as x approaches 4 from the left at this time of f of x. That should be 4 times 4, which equals 16. And the limit as x approaches 4 from the right of 4 of f of x, sorry, equals 4 times 4 minus 32. So that's going to be negative 16. So notice those two don't match, so it's not continuous there. Notice the first one right out the gate says both exist and are finite, but they are not equal. So we do have that, and it does not satisfy the other two conditions, so that means that all of a sudden we are having D go right there. Okay, almost done with this. Now let me switch colors just to kind of give you an eye line here. What is 1 over x minus 4 done? Well, that's shift us 1, 2, 3, 4. You know what the graph of 1 over x looks like. So this is basically shifted it 4 units to the right. Okay, so we have a left-hand limit is approaching negative infinity. So limit as x approaches 4 from the left of f of x equals negative infinity. And then you have limit as x approaches 4 from the right of f of x equals positive infinity. Okay, so notice number 4 says limit as x approaches 4 from the right f of x exists, but limit as x approaches 4 from the left does not. Limit as x approaches 4 from the left is negative infinity. That actually matches our e function. And so finally, last but not least, we can check this, and you can see the limit as x approaches 4 from the right. What do we have? 4x plus 32. So that becomes, so 4 times 4 plus 32. So that'd be 16 plus 32 is 48. However, if we do limit as x approaches 4 from the left of f of x, that's the limit as x approaches 4 from the left of cosine of 1 over x minus 4. So that means cosine of negative infinity, which is a does not exist scenario. And so that is exactly what's said for number 4. Wowzers, I know. A lot of work, but hopefully you can see a lot of people struggled on that one, but that's how you can break it apart and kind of work the whole problem on out. Just taking limits left and right and going from there. All right, we're on to differentiating. So we want to differentiate. We're going to use chain rule left and right. I kind of mentioned you're going to see your exam is going to be that way too. So lots of chain rule and product rule, quotient rule, and all that jazz. So if you take a look at this one, we have e to the 8 to tan square root of x. So first off, the derivative of that would be e to the 8 tan square root of x. But now we need to use the chain rule. So times the derivative of the 8 tangent square root of x. And hopefully you're getting better at this where you might not need to write the ddx part, but I'm just writing it here for the first couple times so you can get the hang of it in case you aren't remembering that part. So now, oops, so this equals e to the 8 tan square root of x times, this would be 8, the derivative of tangent is secant squared. Now we have to multiply by the derivative of that interior function, once again, so which is the square root of x. A lot of you might like that better though as x to the 1/2, right? Because now you can use the power rule, and you can write it as 1/2 x to the negative 1/2 if you like. That's fine, or you can brush this up. We get e to the 8 tan square root of x times 8 secant squared of the square root of x times, this is 1 over 2 square root of x. And that would be a final answer right there. I don't need you brushing stuff up. I just want to make sure I can see your work along the way and things along those lines. So moving on to the next one. And if there are any questions, once again, there's a chat box. You can feel free to post right there. When you're using this one, you have to use the quotient rule to start. So we got to square the bottom. X to the 5th minus 5x cubed, the quantity squared. And then we want to write that down once again. And we're going to take a derivative of that top function. So derivative of the natural log of secant x. Now if we were clever, I'm going to pretend we're not being that clever right now. We could use a property of natural log, so you can write secant x as 1 over cosine of x. And then that's cosine x to the negative 1. You could bring the negative 1 out in front, and you would have an easier, slightly easier derivative. This way we're going to have some things cancel, but that's no big deal. So taking a look now, we have the numerator where we write natural log of secant x. And then times the derivative of the denominator, so x to the 5th minus 5x cubed. Okay, taking a look at this, let's look at the derivatives. So natural log, that makes it 1 over secant x. But now we're going to have to take the derivative of the interior function. The interior function is the secant x. So that makes this times secant x times tangent x. So notice that whole derivative just simplifies to tangent x. Okay. Now for the next part, we'll use the power rule here, so you get 5x to the 4th. And then it goes 5 times 3x squared. So we go minus 15x squared. So this whole thing becomes x to the 5th minus 5x cubed times tangent of x minus the natural log of secant of x, which is actually just the natural log of cosine x, times 5x to the 4th minus 15x cubed. Or 15x squared, sorry. Hopefully I fit all that in the screen. Oh yeah, awesome. Okay, and then all of this is divided by x to the 5th minus 5x cubed, the quantity squared. All right, so we've seen differentiating. Let's try some more. Make sure we can get this down. Let's see here. With our next one, well, let's write it another way first because some people struggle to see this. You can write this as e to the 4x times cosine x raised to the 1/5 power. So notice the outside function is at 1/5 power, and so we can use the power rule to start, and then we'll use the chain rule in a second, along with another rule in just a minute. So this is 1/5 e to the 4x cosine of x times 1/5 minus 1 is negative 4/5. Then times the derivative of e to the 4x times cosine x. This is where a lot of people start to botch up. Okay, this, you have a function here and a function there. That's a product of two functions, so that tells us to use the product rule. What does the product rule state? It says the derivative of f times g equals f prime g plus f g prime. So h prime of x will kind of go through. We'll get 1/5. You could put this down in the denominator, but it's not necessary as long as we see what's going on here. E to the 4x, you get a cosine x. Then you get a negative 4/5. So now we got to use that product rule. So we take the derivative of the first function, e to the 4x, but you got to multiply by that, what's up in the exponent, the derivative of that. So the derivative of 4x is 4, so I'll just put that 4 out in front. And then that's times cosine x, because cosine x is g. Plus, now we write the first function, e to the 4x, and times the derivative of the second function, which is negative sine of x. And now we're just going to close off the parentheses to the whole thing, and we are in good shape once again. Okay, so now moving forward, q of x equals sine of x raised to the tan inverse of x. Uh-oh. So the way to do that, you can't have a variable up in the exponent and in the base, so we take a natural log of both sides. So you go natural log of q of x equals the natural log of sine of x, and then we have an arctangent of x. You could do the e to the natural log trick too. That might be a little bit trickier, but it's not too bad. So now you're going to have to use implicit differentiation. So when you go on the left-hand side, you get 1 over q of x, but using the chain rule, or what implicit differentiation is essentially doing, you have that going on there. Oh, I should write an extra step. You have natural log of q of x equals, what was the whole purpose of taking a natural log of both sides? So you could bring that arctangent on down. So notice now on the right hand side we got to use the product rule. So the derivative of arctangent is 1 over 1 plus x squared. You can just look that up and see it, or we can, if you need to see some of these done, please let me know. Times natural log of sine of x plus, okay, so now we have the arctangent of x. We got to work with this next derivative. So the derivative of natural log of sine of x is 1 over sine of x times the derivative of that interior function. What derivative of sine is just cosine x. Now, in order to solve for q prime of x, we need to multiply both sides by q of x. So q prime of x equals q of x times, notice we can rewrite that first part as just natural log of sine of x over 1 plus x squared. And then cosine over sine, so we have arctangent, oops, meant to draw bigger parentheses here, times cosine over sine is cotangent of x. We can write that off. So what we get here is q prime of x. Now what is q of x? Well, if you recall, q of x, look at the beginning portion, we have that equal to sine of x raised to the tangent of x, arctangent of x. So we have sine of x raised to the arctangent of x, and then times the natural log of sine of x over 1 plus x squared plus arctangent of x times cotangent of x. Woo! It took some work, but we are there. And you've probably seen some of these in your homework and whatnot, so kind of getting a feel for what's going on there. Let's take a look at r of x now. You have cotangent of x cubed, so let's rewrite this. Let's make it a little bit nicer. So you get the cotangent, and now on the inside, let's write this as 3x raised to the 1/7. And then cotangent cubed, right? So let's see if we can break this apart now, all in one shot. So we got to bring that power rule on down. So you get 3, you got cotangent of 3x raised to the 1/7 power, and then that's squared, right? But now we got to look, okay, so what's our next function? Well, our interior function, you have this whole thing, but the cotangent is the driver there, right? Because the other part's inside the cotangent. It's not multiplication, it's inside. So that means derivative of cotangent, which is negative cosecant squared of 3x to the 1/7. Okay, so now where do we go? Well, you have this function inside of here, right? So we got to take the derivative of that. Well, in order to do that, we're going to have to use the power rule. Okay, so we'll get 1/7 times 3x, and then 1/7 minus 1 is negative 6/7. So now, though, we got to go inside there, and we'll see what we have. And so what does that give us? Well, that ends up giving us the derivative of 3x is just 3. And that's our final answer, folks. So that's all there is to it. Now you'll see one that's a little bit different than most. Okay, so we have t of x equals the integral from 4 to x of sine cubed z dz. What is this screaming to you? Well, it's the fundamental theorem of calculus, part 1. And here's how easy it is. When you take this, notice the x, let me change colors real quick. The x is your variable, right? And that appears up in the exponent here. So what the fundamental theorem of calculus says is, hey, if we take a derivative, and that's just x up there, all we need to do is just plug in the x for whatever variable appears inside the integral. That's it. You're done. Nothing else to it. Now you might say, okay, well that's easy. But you got to try some different ones, because what happens is, this is where it gets a little bit trickier. Say you have something like this. Notice the x is not in the top bound, so we have a little bit of work to do. Okay, so what's the work that we have to do? Well, you got to flip the bounds. So you go negative, and then we have integral from 9 to x, and we still have natural log of t cubed minus 7t dt. Still fundamental theorem of calculus part 1 though. So this is z prime of x. But now where's the big difference? It's that negative symbol out in front. So we got to go negative because now x is up there. And now just plug in x in for those bounds. Natural log of x cubed minus 7x. And you're done. That's all there is to it. Finally, we're at a tougher problem. So now when we go w prime of x, what does this equal? Well, when you look at this one, it looks like, okay, everything's hunky-dory. We can use the fundamental theorem, the calculus part 1. So you go e to the cosine of 4x squared minus cosine of x. All right, and we're good. Not so fast. This is where we can't forget about our chain rule. So chain rule says, hey, you can rewrite this as 4x squared minus cosine of x So we can rewrite this thing as cosine of 4x squared minus cosine of x, and now we need to take that derivative. The derivative of that is 8x minus, the derivative of cosine is negative sine. So that makes a positive when you go minus and minus, so positive sine of x. And you're done. So that's the one thing that most people forget with the fundamental theorem of calculus part 1. When the bound is not just x, you just got to use the chain rule. That's it. The rest is the same. You're just plugging in for the variable inside the integral. Okay, all there is to it on those. All right. So now we've seen a lot of derivatives. Let's start to get to some funkier ones. So we have a being f of x equals L of x to the 9th, and L prime of x equals 1 over x. So we have this. What's going on with f prime of x? So f prime of x in this first case, we're going to need to use the chain rule. So you go L prime of x to the 9th, that's just the outside, times, okay, so now we got to multiply by the derivative of the inside. Okay, so notice that makes L prime of x to the 9th. We already know what that is. That's just 1 over, we've replaced the x with x to the 9th, so that's 1 over x to the 9th, times the derivative of x to the 9th is 9x to the 8th, right? And simplifying that, if you want, you can make 9, and then the x to the 8th will cancel off with the x to the 9th, everything except for that last x term, so you're left with 9 over x as your final solution. Okay, so our next one, let's do g of x here. So g prime of x, we go L prime of 4x. And so this should L prime of 4x times the derivative of 4x. L prime of 4x, that's just 1 over 4x, times the derivative of 4x is 4. So your 4's will cancel, and you're left with just 1 over x. H prime of x. Now, last but certainly not least, that's going to be L prime of 1 over x times the derivative of 1 over x, which is the same thing as x to the negative 1. So notice now you get 1 over x times the derivative of x to the negative 1 is negative 1 to x to the negative 2, or negative 1 over x squared. Okay, so this thing becomes negative, well, you can multiply those x squareds, that would cancel off with one of the x's, so you're left with negative 1 over x. And that is your final answer. And we're done there. Questions on that one? So hopefully you're seeing a wide variety of derivative problems. We'll get to integrals in time. So if we want to find an equation of the tangent line to the curve at the following point, how do we actually go about doing this? We know that, so actually, let me call this, just to change it just slightly, let's call this f of x. We know that f prime of 0 is the slope of the tangent line. So if we can find f prime of x, we're going to be in good shape. And the way we do that, we go 10 goes 1 plus 4x raised to the 9th times the derivative of the inside, so times 4. Right? So now, what do we do? Well, f prime of 0 should be, well, I can make 4 times 10 makes 40. 40 times 1 plus 4 times 0 raised to the 9th, so that should be 1 to the 9th, so this equals 40. So now we have a point on the line, so this goes y minus our y1, which is 1, equals 40 times x minus x1, which is 0. So notice y equals 40x plus 1. And you're done. All right. So now we want to find y prime by implicit differentiation. Don't worry about the matching, what goes on there. So implicit differentiation says we differentiate with respect to x on both sides. So differentiate with respect to x is 6x sine of y and then 7 sine of 2y and equals 7 cosine y. And actually pretty much all these are the same, so I'll only, unless you want to see them all, I'll do just one to kind of speed up the process and get to some of the other problems that'll be a little bit more important. So when we do this, you got to use the product rule. So you get derivative of 6x. I could technically pull the 6 out in front if need be, but not necessary. Plus 6x times the derivative with respect to x of sine of y. Plus, so 7 sine of 2y, we can use the chain rule here and all that jazz. So we get 7 cosine of 2y times the derivative of the inside, which is going to be 2, but then since it's a y, we need to put dy dx, or y prime works just fine. And then equals the derivative with respect to x of 7 cosine of y, so that'll be 7 sine of y times derivative of the inside, which is y prime or dy dx, right there. Now, and you'll see why I'm going to run out of room just on this one problem alone. So that's why we'll just cover this one. And the rest you can try. You have this problem in your homework. They all kind of follow the same suit. So this is 6 sine of y plus 6x cosine of y times dy dx plus 7 cosine of 2y. Oh, I'm sorry, 7 times 2. Let's make this a little bit easier on ourselves. That's 14 cosine of 2y times dy dx equals 7 sine of y times dy dx. All right, wowzers, right? Everything has dy dx except for the 6 sine of y, so we'll isolate the 6 sine of y on one side, and then we'll have 7 sine of y dy dx. And notice dy dx is raised to the first power. That's going to be good for us because we're going to be able to factor it out here in a second. That's the whole process going on here. 6x cosine of y dy dx. And then minus 14 cosine of 2y dy dx. So notice this makes 6 sine of y equals, factor out the dy dx, and then you get 7 sine of y minus 6x cosine of y minus 14 cosine of 2y. So the way to solve it from there is to divide both sides by what's appearing multiplied by dy dx on the right hand side. So you get, for this part, all of the others are going to be slightly different, just a slight variation. Dy dx equals 6 sine of y divided by equals 7 sine of y minus 6x cosine of y minus 14 cosine of 2y. And that's your final answer. Okay. If you wanted to try the others, the only difference in the first one, you just changed the signs and cosines. Everything else is going to be the same. So you'll just have some negative symbols appearing here and there where they were once positive, and the negatives that were before will turn to positive. So, oh, actually, I made a mistake. I got to apologize. I didn't catch it. I'll highlight it right here. Cosine of y. That's negative 7 sine of y. So that makes negative 7 sine of y. that makes negative 7 sine of y. That makes negative 7 sine of y, right? And so this should be negative right there. My apologies there. So, yeah, you got to be careful. That's the only thing. With the other ones, you're going to have the negatives and positives flip. So my apologies for forgetting that negative. But as soon as you see that, you can work that problem out and kind of get going. Be good to go. All right. So we got the process down. All right, so now same thing here. We'll just kind of focus on one of these and then worry about the other. So we have an aircraft is flying at 390 feet per second with an elevation of 185 feet from the ground on a straight line path. Okay, so that's pretty useful to us. That'll take it directly over the aircraft and an aircraft gun. So you have an aircraft, it must be going from the drawing here, it's going in this direction. This is 185 feet, it's not changing. Okay. So how fast in radians per second will the gun have to turn accurately to track the aircraft when the plane is 1,000 feet away? So you have this x. Okay. So the real thing that we want to try and do is set up a nice equation and use the information we have. So the information that we have is the aircraft is going in the x direction. So we have dx dt, assuming that direction is positive, is equal to (390 feet per second). Okay, and you might say, well, why can we say that if x is down on the ground? Well, notice you can draw the same triangle with the corresponding angle just up here, right? So keep that in mind. You're going to be able to get away with that. Now, you might want to call it negative, or just depending upon how you're looking at this. How fast in radians per second will the gun have to turn accurately? So we're looking for d theta dt. All right. So this one actually isn't, it looks scary, but it's really not too bad. So what's kind of the best format to set this up? Well, notice we have x in the 185. So if you go x over 185, what does that equal? Well, that should equal so that's adjacent over opposites. That would be cotangent of theta. So looking at that now, we want to try and find an answer. Okay. All we need to really do is take a derivative with respect to t. So d dt of x over 185 equals d dt of cotangent of theta. Okay, so moving forward from there, we get 1 over 185 dx dt equals derivative of cotangent theta is negative cosecant squared of theta times d theta dt. Okay, so this looks really scary at first, but then think of what's cosecant theta. So first off, we can move this, well, let's write it this way. 1 over 185 dx dt equals, this is negative 1 over sine squared theta d theta dt. So notice our d theta dt, we can find a solution here. You get 1 over 185 dx dt times negative sine squared of theta. Okay, we know dx dt, that's 390 feet per second. All right. So how do we get that other information, that negative sine squared? What's going on there? So in this case, we have 185 and we have 1,000. Right? So that means that this side right here would be the square root of 1,000 squared plus 185 squared. Right? And so when we're talking about sine of theta, we can get that answer. And so I'll kind of move that over. And so for the 1,000 feet away, you go 1 over 185 times 390, which isn't so bad. Those two things will cancel. No, they won't. Actually, that's not perfectly lined up. And then times negative square root of, oops, the square root will appear in the denominator. Up in the numerator, we'll have the opposite side, which is 185, negative 185, over the square root of 1,000 squared plus 185 squared. And that will equal d theta dt. Notice that the 185s will cancel, and you're left with negative. Now, how fast in radians per second? So negative is referring to going the other direction here, so we're going to try and track it. So you can actually turn it to positive if you want, to talk about how fast. So we'll drop that symbol in terms of our final answer, that negative symbol. Whoops. Sorry about the battery running low. Let's charge this back up. Okay, so our final answer here, we get 390 over the square root of 1,000 squared plus 185 squared. And taking that to the second answer, notice the only place 1,000 really came into play was on the denominator, and so this one would be 390 over the square root of 100 squared plus 185 squared. And if it's talking about the direction of the angle, you put the negative to kind of counteract what's happening, right? So yeah, just kind of keep that in mind, because we chose positive x to be the direction approaching that, and so that means the x value is getting smaller, so this theta will be getting larger if we're writing that as negative, just from the direction we chose our x to be. All right. So let's see what's happening here. Suppose that 3 is less than or equal to f prime of x is less than or equal to 5 for all values of x, and it says use the mean value theorem to find values for the inequality below. So what we know is the mean value theorem. And so we're going to assume that this is actually continuous and differentiable. So the mean value theorem says if it's continuous differentiable, then you have this property holding. There exists a C such that this would happen we would know that f of 6 minus f of negative 2 all over 6 minus negative 2, there'd be some place where C would equal this, right? Well, if we know it's bounded, what we can actually say then is that, hey, if the derivative is bounded, we know 3 is less than or equal to f prime of x. Well, that should be f of 6 minus f of negative 2 all over 6 minus negative 2. And so the mean value theorem on this interval, I should say, negative 2, 6. And this is less than or equal to 5. Well, notice this makes 8 on the bottom, right? Well, let me highlight that in a different color just so you can see that's 8 and not a delta. So multiply both sides by 8. Notice you get 24 less than or equal to f of 6 minus f of negative 2, and that's less than or equal to 40. So your values are 24 and 40, and there's your using the mean value theorem. Alright. Okay, so let's get crazy on this one. This is another related rate problem. You have a conical water tank with vertex down, has a radius of 13 feet. And 20 feet to the top of that. Okay, so you have this thing going right here. And we know that this has a radius, so if you have the circle right here, this is 13 feet, and then we know this distance is 20 feet. Okay, so we're going to try and figure out, but the water is only filled to some certain level right in here, right? And this is changing all the time, so this is going to be some R and some H, where H is right there. Okay, so you're having this water fill like so, and we want to figure out the depth of the water is increasing when the water is 14 feet deep. So the first thing, I mean, when you're looking at a volume of a cone, you're looking at the formula is pi over 3 times r squared times h. Okay. You can think of that cylinder would be pi r squared h, because you get the circle pi r squared times the height. This is you can think of it as a third, but I mean a little bit more to it than that, but it gives you an idea as to how it's going. So now what we want to do, using some of that information, we're going to try and use related rates, so we got to start taking the derivative with respect to t. But notice r squared and h are both variables, so we need to use the product rule. And so we'll go d dt of r squared times h plus r squared times d dt of, let me bracket that, of h. Okay, everything might seem hunky-dory right now, but it looks like we're going to run into a problem, and I'll explain what that is in just a second. So notice this becomes 2r dr dt times h plus r squared times dh dt. Now, from the information that we have, what are we looking for? And I should have written that first. How fast is the depth of the water increasing? So that tells us that we're looking for dh dt. Okay, so we're looking for dh dt. What else do we have, right? And so we know that this 10 cubic feet per minute, that stands for dv dt. That equals 10. So we can fill that in. That's 10. But here's the problem. We don't have anything else, right? So we need to do some work here, and how are we going to solve this? Well, notice you have a triangle. The first one is 13, and then that whole distance right there is 20. Okay. And inside of that, we have some blue going on, and we have R and H. So what that means, since this is similar triangles, right, because you have the same angle here and here, okay, we can go 13 over 20 equals R over H. Or if we wanted to, we could replace this. This becomes whichever one we want to solve for h, so let's try and get h on one side. So we get h equals 20r divided by 13. Or I'm sorry, yeah, we want to solve for, yeah, that'll work. Okay. So notice when we take this and we want to try and get rid of this dr dt, we get dh dt. Well, well, I'm sorry. So we're trying to solve for dH dt. I actually did that backwards real quick. Let's try and solve for r so we can put everything in terms of h. So notice that would make r equal to 13 over 20 times h, right? So that means dr dt equals 13 over 20 dH dt. So now we can try and work this out. This is 2 times r is 13 over 20 times h. dr dt is 13 over 20 dH dt, and then we have another h right here, plus r squared, that would be 13 over 20, and then this would be h, the quantity squared, and a dH dt. Well, that's convenient. So notice, let's take a look real quick. You have two h's, that makes an h squared. You have a 13 over 20 and another 13 over 20, which makes the 13 over 20 h squared. So you have 13 over 20 h squareds in both parts and a dH dt. But you have 2 of those here, and then you have 1 of those right here. Okay, so 2 plus 1 of those makes 3 of those. So notice this is 10 equals pi over 3 times 13 over 20 h, and we're squaring that part, and then times dH dt. Notice now the 3's will cancel, and so this gives us, we need to find what h is. H is 14 feet is the time we're looking at, so h equals 14, so you get 10 equals pi times 13 squared times 14 squared, all divided by 20 dH dt. So notice if we solve for dH dt, all we need to do is multiply by the reciprocal, and so you get 10 times 20, all divided by, you get a pi down below times a 13 squared. Oh, I'm sorry, I forgot 20 squared. So that's a 20 squared. Thank you. So you have 13 squared times 14 squared. And that's a good final answer. I mean, that gives us the idea of what's going on there. That's what I'm looking for. Questions on that one? I know related rates give people some trouble from time to time, so wanted to cover that, and I wanted to cover optimization, and I tried to look for the one that gave people the most trouble, and so it was the blood vascular one. So the blood vascular system consists of blood vessels, arteries, arterioles, capillaries, and veins that convey blood from the heart to the organs and back to the heart. So this system should work so as to minimize the energy. So we're trying to minimize something here. Minimize the energy expended by the heart in pumping the blood. This energy is reduced when the resistance of the blood is lowered. One of, I'm going to horribly mispronounce this, Poiseuille's laws gives the resistance R of the blood as R equals C times L over R squared, where L is, okay, this is important, L is the length of the blood vessel, so that's talking a distance. R is the radius, okay, so that's convenient there. And C is a positive constant determined by the viscosity of the blood, so this is just a constant. So the C is not doing really much at all. Okay, the figure shows a main blood vessel with radius R branching at an angle theta into a smaller vessel with radius S. Oh, okay. So I was looking for the S and R. It says that that's respectively R1 and R2. So we'll kind of deal with this here and see what we can do. Okay, so the first part says use Poussey's law to find the total resistance of the blood along the path ABC. This C is different, so it's not the constant. So not constant, just point, just a point. So don't confuse that. These two C's are not the same. Where A and B are the distances shown in the figure. Okay. So taking a look at this is going to be tricky, but I think we can do it. So we got to try and work with what we have here. So I'm going to actually draw some triangles. So we have one triangle sitting right here, and that triangle is quite important. And notice we have an R1 and an R2 going on there. So first off, let's actually do the distances that we want. So we want to do this distance right here. And then this is, so we'll start here, and then we'll need that other value. So when we start with this R, the resistance of the blood, we're going to have a C over R1, or no, in this case it's R2 squared. But keeping that in mind, here's the tricky part. We need to find the length of that blood vessel. So what the heck is that length of the blood vessel? So what we need to do is find the length of this. Okay. So in order to find the length of that piece right there, notice R2 really won't play a role. It already did with just the radius that we were talking about. It's the radius of that blood vessel. So now what happens is we got to find the length, and the only information we have is this B and this theta. But notice that length is the hypotenuse. So you could do always B over, let's call it the hypotenuse, equals just the sine of theta. So if we're solving for the hypotenuse, that equals B over sine theta, or another way to say that, that's equal to B times cosecant of theta. So this is just B cosecant theta. So that's that first part. Now, let's handle the second part, because we need this distance. But in order to get that distance, we're probably going to need this distance right here. And the way we can get that is, so first off, for this distance, we can go B over adjacent equals tangent of theta. So that means that when we solve for adjacent, we get adjacent equals B over tangent theta, which is just B cotangent of theta. Okay, so this will be C over, now what we're looking for is R1 squared, right? We're dealing with this. So notice we got to take that distance and subtract it from this whole distance, A. So this should be A minus B cotangent theta. And so that's our formula that we're talking about. So we get C over R2 squared. Now they're talking about using different symbols, but you can kind of see what's happening. B cosecant theta plus C over R1 squared, A minus B cotangent theta. Alright. So now it says find the value of cosine theta which minimizes the resistance. Holy mackerel, how do we do that, right? So the way we're going to solve for this part, I'll start that up here. We're going to need to take the derivative of r with respect to theta. Okay. So notice the C and the R2s and all that stuff, they're all remaining the same. They aren't changing. We're just changing the angle here. So really all we have is we have C over R2 squared times b, and the derivative of cosecant is negative cosecant theta, cotangent theta. A is just a constant, so that derivative will go to 0. So we get plus c over r1 squared. And we have a negative negative. The derivative of cotangent is negative cosecant squared. So you'll get a negative times a negative makes a positive. So this will be b cosecant squared of theta. And what do we do with this to try and solve it? Well, first off, actually, we can do a couple things. We could factor out a b cosecant theta. Okay, so I'm going to write that here. So you set this all equal to 0, right? And let's factor out a b cosecant theta. What does that leave us with? Well, that leaves us with, we can also factor out a c. So we'll go c times b cosecant theta. We're left with 1 over r2 squared times cotangent theta. And I should say negative 1. Plus 1 over r2 squared cosecant theta. Okay, wowzers, right? Okay, yeah, so this works out nice. Another thing you can factor out, cotangent theta is cosine theta over sine of theta, and cosecant theta is 1 over sine theta, right? So you can make this 0 equals c times b. If we factor out the 1 over sine theta again, what are we left with? Well, we're left with cosecant squared theta, and then what we have is negative 1 over r2 squared. This is cosine of theta, plus 1 over r2 squared. Oh, that's beautiful right there. Okay, we're in great shape now, because notice this does not equal 0. So this cannot equal 0. Okay, so the first part can't equal 0, so we only set this second equation equal to 0. And so we get 0 equals negative 1 over r2 squared cosine theta plus 1 over r1, or I switched them up. Which one was r1? So sorry about that. I should have had r1 squared. I kept on writing r2 in the wrong spot. So those are r1 squareds. Okay. So move that over to the other side. Notice we get 1 over r2 squared cosine theta equals 1 over r1 squared. And holy mackerel, we solve for cosine of theta. Cosine of theta equals r2 squared over r1 squared. We didn't need an a, b, or c. It's actually really a simpler way for us to write that is r2 divided by r1. Just that whole quantity squared. Wowzers, that's pretty crazy. So yeah, so looking at that, and I should check to make sure this is a minimum and not a maximum. That's not too bad. You go back to this equation, probably right here. So I'll mark this as a star. Notice if cosine theta is less than r2 over r1, that means the negative is not going to be as large as or the negative will be, so if that's less than r2 squared over r1 squared, then the r2 squareds wouldn't quite cancel. It'll make the negative a little bit larger, so we'll have something decreasing in that value. So yeah, so we'd have decreasing to increasing, which means we've got a minimum going on there. Okay. Woo. So this is some work here now. So the last part, it says find the optimal branching angle when the radius of the smaller blood vessel is 1 over 1, 1 to 1, the radius of the larger vessel. So basically they're same size. Okay, so that means that cosine of theta equals 1 over 1 squared. So that means cosine of theta equals 1. So that means theta equals 0. If you had, like, say 1/2, then you're looking at the pi over, in that case would be pi over 3, I believe. Yeah, for 1/2, and then if you had square root of 3 over 2 or something like that, or you know, then you'd be dealing with like a pi over 6. So you have some different examples here, but that one's a 0. And so what that's saying is, if they're the same size, you should have basically a flat line all the way across to try and get that, minimize the energy, so forth. All right. So now we're going to use some of the information before, all these derivatives and things like that, limits, to try and find a nice solution to this. Sketch the graph of the curve. So the first thing you should always do, and this one it isn't going to make much of a difference, but we'll start with the domain. It's a polynomial, so this is negative infinity to positive infinity. Then for the other portions, you can find the intercepts, you can find the limits. I'll actually jump, well, I can do y-intercept pretty easily. So the y-intercept, notice you get f of 0 would equal 0 cubed minus 6 times 0 squared plus 9 times 0 plus 1. And so that whole thing equals 1. Alright, so now we have that. So 0, 1 is on our graph. The x-intercept, let's take a look. That's not going to be so obvious right away. So there's a rule of signs. So Descartes rule of signs. How many flips of these signs will tell you how many positive zeros. So in this case, you have one flip from positive to negative, and then another flip. So that you're going to either have 0 to positive x values. It'll be negative, and then you can check and see that you plug in f of negative x, and you can determine, and that looks like it'll be, so that'll be negative, negative, and then positive. So one flip. So actually, there will be one negative root. In the rational root theorem, I can plug in 1, and notice I don't get a solution. So I got to figure out another value. But we know that f of 0. So I'm going to try and approximate this value is what I'm getting at. So f of 0 equals 1. So now I know there's going to be a negative root. I don't know about the positive, and we'll take some other information to check the positive. Let's start with f of negative 1, just for kicks. Okay. So if you plug in f of negative 1, what do we get? We get negative 1, the quantity cubed, minus 6 times negative 1 squared, plus 9 times negative 1, plus 1. Okay, so that means that this gives us what? Negative 7, negative 16, negative 15. All right, that's good. Okay, so by the intermediate value theorem, there exists a root on the interval 0 or negative 1, 0. And since it isn't those values, I can make it an open parentheses. Let me distinguish. That's not the point on the graph. That's on the interval. Actually, I will go back to square brackets just for kicks. That way you aren't confusing it with the coordinate system. It's not a coordinate system going on there. So actually, if I wanted to be a little bit more precise, the way you can kind of just start to get an idea for where the roots actually occur, you plug in the halfway point. And so notice now we get negative 1/2 cubed minus 6 times negative 1/2 squared plus 9 times negative 1/2 plus 1. And let's check out what happens here. Well, notice you're going to get negatives all the way across, right? Because you're going to get negative 1/8 And then you're going to have negative 6 times 1/4, which is still some number. When we go 9 times negative 1/2, notice that is still larger than, in terms of the negative being larger. If you take the absolute value, that's going to be bigger than negative 1. The key is that this is negative. So that tells us, by the intermediate value theorem, we can change this. And so then the next step, we can say, even better, we know it's going to be, since we switch from negative to positive, negative 1/2 to 0, we know that's where our root has to lie. And you can do negative 1/4 and keep on going, but at least you've got a really good idea as to where this intercept is going to occur. Okay. All right. So now, moving forward, we got those. We got to do our limit as x approaches infinity of f of x. Well, that might take a little bit of work, but it's not going to be too bad. That's the limit as x approaches, because you got infinity minus infinity plus infinity. What the heck does that do? Well, let's rewrite this. Just write it as x squared, and then we can go x minus 6 plus 9x plus 1, and that'll tell you right away that you're going to have infinity times infinity plus infinity, so that whole thing makes positive infinity. Limit as x approaches negative infinity of f of x. Ooh, can we use the same? Yeah, looks like we can use the same, I believe. So negative infinity squared is going to make positive infinity, but then when you go negative infinity minus 6, it's going to be negative infinity. So that first part's negative infinity, and the second part is negative infinity. So negative infinity minus infinity, that'll still remain negative infinity. And so this whole thing is just negative infinity. Alright, so we got most of the information about the function because there's no asymptotes or things like that to check out for. Now what we need to move on to, and we'll do this in blue, is the derivative. Okay, so first off we got to take the derivative, so that's f prime of x equals, we get 3x squared minus 12x plus 9. Alright. Factor out a 3 from that. We aren't going to have any place where it doesn't exist, but we will probably have a place. X squared minus 4x plus 3. Oh yeah, there we go. So we're going to have a place where this thing equals 0. So notice you can factor this. This is 0 equals 3, and then you get x minus 3, x minus 1. So you get x equals 3 and 1. So that means when we do this, we can have 1 and we can have 3. We know that these are the x's, this is the f prime of x. So you have zeros going right here. And then, let's see here, our intervals, negative infinity to positive 1. Then we have from 1 to 3 is our next interval, and then from 3 to positive infinity. From negative infinity to positive 1, what are we looking at? Well, you're going to plug in a number that fits inside of there. 0 works great. So notice 0, when you plug that in, you get a negative and another negative. That makes a positive. And so that tells us it's increasing on this interval. Okay, moving forward from there, what do we have? We have 1 to 3, pick the number 2. So you get negative when you go 2 minus 3, and then you get positive when you go 2 minus 1. So negative times a positive makes a negative. And then, let's see on the next one. Pick a number in between 3 and infinity. Let's try 5. 5 minus 3 is positive. 5 minus 1 is positive, so this whole thing is positive there. So we go increasing to decreasing to increasing. Now the other thing we can do with those critical points, we can plug those into the original function. F of 1, what is that going to equal? Well, you get 1 cubed minus, well, let me figure that out, minus 6, and then plus 9, and then plus 1. Alright, so this is going to be So that's 10, 11 minus 6, that's 5. Okay, so you have the point 1.15 on the graph. F of 3 now. So 3 cubed, which is 27, minus 6 times 3 squared. So 6 times 9 is 54. Plus 9 times 3 is also 27. Oh, that's going to be nice. And so this is kind of funny, because 27 plus 27 makes 54, minus 54 makes 0, and then add the 1, so you get 3 comma 1. So we have a few points on our graph, and let's kind of get towards our graph, and I'll rewrite the function here in a second. Okay, we're going to assume that each unit is 1. Okay, and let's try and, well, actually I'll redraw this down here. The thing I usually like to do is line it up if you have a graph coordinate system. So here's 1, 2, 3, and then there's 3. Okay, and we knew that we went positive, so this is for the f prime. We went positive, negative, then positive for that whole interval, and it was zeros right there. Okay, so we also had, what was it, f of, we had 1, 5 and 3, 1. So 3, 1 was a point on our graph, and 1, 5, so 2, 3, 4, 5. And then I believe we also had 0, 1. So all those are points on our graph. And we're going to say I have some other intercept that's inside of 1/2, so it'll be something maybe right in here. Oh no, did not mean to do that. So just inside of 1/2. Okay, or negative 1/2 I should say. Now what was our, we had our first derivative, we already taken care of that. 3x squared minus 12x plus 9. So first derivative was 3x squared minus 12x plus 9. It's time for the second derivative. So that'd be 6x minus 12. Oh, that's going to be nice. So that means when we set this equal to 0, we get in this case it would be 0 equals 6x minus 12. So x, you can add the 12 over to the other side and divide by 6, so x equals 2. So that means when we're looking at the graph, I'll put this in pink. Got 2 going smack dab in the middle. And that's going to be an f double prime sitting right here. Now when we go 6x minus 12, you just pick something from the negative infinity to positive 2, so pick, say, negative 5. And notice you'll get a negative number. So that means it's concave down on that interval. And then it's 0 here. And then at 2 to infinity, pick a number, say 7. That's going to be 6 times 7 is 42, so that's going to make this positive. So we're going to be concave up the rest of the way. Now the other thing we should do, just to get in for kicks, x cubed minus 6x squared plus 9x plus 1. So x cubed minus 6x squared plus 9x plus 1, that was f of x. So now we should also find f of 2. So notice it's going to be 8 minus, so it's going to be 6 times 4, which is 24, but then plus 18. And then plus 1. So 8 plus 18 makes 26, and then plus another 1 is 27. 27 minus 24 is 3. So we can go on the graph, and at the point 2, go 1, 2, 3 units, and there is going to be our point of inflection. Right? And now we also know the other information that we had is the limit as x approaches positive infinity of f of x was positive infinity. The limit as x approaches negative infinity of f of x was equal to negative infinity. Okay, So I think we're ready to draw the graph now. So we're going to be coming from negative infinity. I'm going to do a quick double check here. By the time we get, just see what f of negative 1 equals. We had it on the other page, I believe. F of negative 1 was, what was that? Negative 15. Alright, good. So I'm really steep right here. And that's supposed to be a straight curve. And notice we're increasing concave down this whole time. Okay, and so we hit here at this point, and this should be a little bit smoother. Sorry, it's hard to draw with the pen sometimes, but hopefully you get the gist. So now we're going here, and we're still concave down like a frown, but now we're going to switch to concave, concave up like a cup. Hit that point right there. So we were concave down, increasing, and we switched at 1 to decreasing, if you noticed. And now we're at 3. We're going to go to increasing concave up the rest of the way. If you plug in 4 into that, notice you're going to get, what is that, 64 minus 96 minus 54. Yeah, you're going to be off the charts again. So we're going to go right back up. That's not accurate where I hit there, but you get the gist. And there's our graph. So we sketched the curve without using a calculator. That's the main thing. We can get the pertinent information without using it. So kind of a neat little trick in terms of what we're able to do and accomplish. Alright. So moving from there, we're going to move into integrals. Real quick, we're going to start with what does it mean to be an integral. So first off, we have the integral from 0 to 2 of g of x. What is that looking for? That's just looking for this area that we shaded in here. And it's looking for signed area. So this is actually considered positive, or net area, or whatever you want to call it. So this is a triangle. So the base of that triangle is 2. So 1/2 times 2. And the height of that triangle is 4. So that should equal 4. Okay, now the integral from 2 to 6, notice this is actually negative, right? And the radius, let's see how many units is that, the radius equals 2. So notice this is 1/2, but we're going to have, it's a half a circle, that's why. And then we have negative 1/2. Pi r is 2, and then we're squaring that. So that makes negative 1/2 for pi, so that makes negative 2 pi. Now we're almost there. So in order to do this, this integral, we can go the integral from 0 to 2 of g of x dx plus the integral from 2 to 6 g of x dx if we need to. And we already have those two pieces of information. Those are 4 and negative 2 pi. And plus the integral from 6 to 7 of g of x dx. So this becomes 4 minus 2 pi. And then, last but certainly not least, let's get this net area right here. Well, notice this is 1 by 1. And so plus 1/2, our base is 1, our height is 1. So that's 4.5 essentially. So we get 4.5 minus 2 pi. And that's our final solution. Alright. So now, trying to tie back in the fundamental theorem of calculus part 1 in a different sort of problem that people had a little bit of difficulty on.